In emission spectroscopy, lambda max is the wavelength of photons, particles of electromagnetic radiation, of which the substance is emitting the most of.
Electrons absorb photons of discrete wavelengths, and these photons have specific energies, given by E equals hc over lambda, where h is a constant and c is the speed of light. When an electron is excited, it absorbs a photon of specific energy that increases its own energy to one of its discrete energy levels. When it relaxes, it emits a photon of a specific energy to decrease its energy to one of its discrete energy levels.
The energy levels available to electrons are unique to each element and are determined by an element's location on the periodic table. Because an element's row on the periodic table indicates the number of electron shells it has, and its column indicates how closely the outer shell is pulled in towards the nucleus because of the amount of protons in that element.
Consider a scenario in baseball where there is a runner on third base, and we assume it takes the same specific amount of energy to hit the ball to and throw it back to the home plate from each of the following regions: immediately in front of home plate, the infield, the outfield, and out of the park. For example, it would take very little energy to bunt the ball in front of the pitcher, and very little energy is required for the pitcher to throw that ball back to home plate to get the runner out. In order for the ball to be hit to the shortstop or beyond, a greater amount of energy is required to send it there, and therefore a greater amount of energy is required for the fielder to throw the ball back to the plate.
Similar to how the baseball was hit into discrete regions, electrons exist at discrete energy levels. Once an electron is in an excited state, it's energetically favorable for that electron to return to its ground state, or in baseball terms, to return the ball to the home plate to get the runner out. To do this, the electron must emit a photon or photons of specific energies, and therefore specific wavelengths, that sum to exactly the amount of energy that the electron originally absorbed.
Using these ideas of discrete energy and specific photons, we can build an explanation of color. When we say a substance is a certain color, it's emitting photons of a range of wavelengths that correspond to a specific color in the visible light spectrum. For example, a substance that is observed to be red would primarily be emitting light in a range of 610 to 700 nanometers. Since lambda max is the photon with the highest emission, it would fall into that range of color, but it's not necessarily what determines color, as an emission spectrum like the one shown on screen will show that color is a culmination of all the light being emitted.